Multivariable Calculus, Section 12.8, Directional Derivatives and the Gradient. Here's a picture of some vector fields that we will be studying in multi-dimensions later. According to Wikipedia, the gradient in mathematics, the gradient is a generalization of the usual concept of derivative to the functions of several variables. If f is a differentiable function of n variables, its gradient is the vector whose components are the n partial derivatives of f. It is thus a vector-valued function. So here's a picture of a surface in x, y, and z. So we have a function of two variables, which in this case is the opposite of that quantity. And down at the bottom on the xy, beneath the xy plane, because this surface is below the xy plane, we see a projection of all the gradient vectors onto a plane. Now the gradients then are made up of the two partial derivatives, and we can write it in either of these two notations. And so at a specific point, we would plug in the values a, b, and c of that point, and we would get a particular vector, which would look something like that. And the vector, I've made it a little bit bigger than it really is. And that vector is parallel to the xy plane, and it has been projected down onto the plane below the surface. And there's a level curve for you at the same level as the point ABC. So more on gradient vectors, let's look at some notation. Given vector x to the point x1, x2, and so on, as many variables as we want, and a function of those n variables. And don't panic, because we'll mostly be looking at functions of 2 and 3 variables. But theoretically, we could have as many variables as we wanted. Define the gradient vector of f of vector x to be the partial derivatives of each of the n independent variables. For example, if we have a function of 2 variables, then the gradient vector is, the components are the partial derivative with respect to x and the partial derivative with respect to y, and we can use Newton's notation or Leibniz notation. If we have a function of 3 variables, then the gradient vector has the 3 partial derivatives as its components. Now, some interesting things about the gradient vector that we'll look at in more detail later is that the gradient vector points in the direction for which f increases most rapidly. The length of the gradient vector is the rate of increase of f in that particular direction. And we'll look at this in more detail in just a few minutes. Now notice also that if we want to evaluate the gradient at a particular point, the notation we use is the upside down triangle f of p, where p is the particular point with the values that we plug in for our independent variables into the formula for the gradient vector. Gradient vectors in 3D. The partial derivative of z with respect to x is the rate of change in z parallel to the x-axis, in the direction of I, in other words. And the partial derivative with respect to y is the rate of change in z parallel to the y-axis, that is, in the direction of j. So for example, if we have z equal x squared plus y squared, then the gradient of f or z, you can use either letter, is going to be the partial derivatives with respect to x and y as the components, which in this case are 2x and 2y. So here are some level curves of that surface on the xy plane. And for example, at the point 3, 4, 25, the gradient vector will be 6, 8. And so we will draw a vector at that point moving 6 to the right and 8 upwards. Looks something like that. At another point, we have, say we have 2.5, 0, 6.25 on a level curve. Then the gradient vector is again 2 times x and 2 times y, which in this case would be 5, 0. So we're going to draw a vector at that point. Notice we're not using the z value because these are level curves, so we're just drawing them flat on the xy plane. And so we want a vector pointing 5 units to the right and not pointing up or down at all. And there it is. Now you may notice something that we're not going to prove, the proof is in the book, that the gradient vector is perpendicular to the level curves. In other words, if we drew a tangent line at those points, then the gradient vector is perpendicular to those tangent lines, and therefore we call it perpendicular to the curve. Now if we continue that into 4D, the same idea, which is much harder to draw, we have the partial derivative of w with respect to x is the rate of change in w parallel to the x-axis, again, still in the direction of I. Partial derivative of w with respect to y is the rate of change in w parallel to the y-axis, so in the direction of j. And the partial derivative with respect to z is the rate of change in w with respect to the parallel to the z-axis, so in the direction of k. So if we look at the level surfaces of w, the gradient vectors will be perpendicular to the level surfaces. So if we replace w with a constant, then we'll get a surface, and the gradients can be used as perpendicular to those individual surfaces. For example, let's say we have this function of 3 variables. Then the gradient vector for w has the components of the 3 partial derivatives, namely 2x, 2y, and negative 2z. And if we plug in numbers for x, y, and z, that gradient will be perpendicular to any of the surfaces described by a constant equal to x squared plus y squared minus z squared. Now we're going to go back and talk about the meaning of the gradient vector pointing in the direction of greatest increase. So for example, I'm going to go back to a function of a single variable to try to get the idea across, and then we'll look at a surface. So this is a curve, and it's described by 1/4 x squared plus 2. Now if we look at a particular point, an example, at 2, 3 for example, then the gradient vector is just the partial derivative with respect to x, which is really just the derivative. There is no partial derivative because there's no other part. There's only one. So the derivative is a half x, and if we evaluate that at the point 2, 3, we only put the 2 in for the x, we get 1. And so our gradient vector, if we were going to use it, which we don't actually use it in these two-dimensional examples, it would be the vector I. And so it would point to the right. Now, what does this mean? Well, that means if x moves to the right, so our gradient vector is parallel to just the x-axis, because that's our independent variable, then if x moves to the right, y is going to increase. And there's no meaning here about greatest rate of increase, because it's either going to increase or not. So there's only one option. It'll either increase or not. So in other words, as x moves to the right, y increases. And there's no most, because there's only one choice here. But when we move on to 3 dimensions, then we have more choices in the way we can move. On a curve, all we can do for x is move right or left. We can't move in any other direction. So if we have a surface, then the gradient vector has 2 components, and at a particular point it's a vector something times I plus b times j, and the a and b would be the partial derivatives evaluated at the point. So for a particular point, if you look at this, we've got all kinds of different ways that x and y can move. They can move along any vector parallel to the xy plane. So we've got lots of choices. Which way should x and y move if we want z to increase the most rapidly? Well, you would want to move so that you'd be moving up towards that little pointy thing. You wouldn't want to move x and y, for example, to the right, because then z would be decreasing. And so if you find the gradient, then the theory is that the gradient will point parallel to the xy axis, how x and y should move in order to make z increase the most rapidly. So in this case, if x and y move in the direction of the gradient vector at P, z will increase more rapidly than if x and y move in any other direction or along any other vector. Okay, so let's look at some applications of the gradient vector. Here we have a level surface, and we like to study surfaces independently of the fact that they might be level surfaces. And there is there's a curve drawn on the surface, and the curve could be named by a vector function of t. Now, if we draw the tangent at a point p0, the green arrow is the derivative at that particular point, and it's tangent to the curve. And then that black vector, which is perpendicular, could very well be the gradient. The gradient is going to be perpendicular to the surface, and therefore perpendicular to the plane that's tangent to the surface, as well as the velocity vector. And so we can use, therefore the gradient vector is normal to the surfaces of the function of x, y, and z set equal to c. It's like a level surface, but we're looking at it independently. And so we can use the gradient vector as the normal to the plane or to the surface, and we can write it in either of these notations. Now here's another application. Let's say we have two surfaces and they intersect at that red curve. We've got the blue curvy surface and then we've got a green curvy surface, and we're interested in the intersection, the curve of intersection. So let C be the curve that is the intersection of two surfaces, G of xyz equals 0 and F of xyz equals 0. Well, we know that the gradient for G is perpendicular to the green surface, and the gradient for F, the gradient vector for F is perpendicular to the blue surface, and therefore they're both perpendicular to that red curve. Both gradient vectors are perpendicular to their respective surfaces, and therefore both are perpendicular to C. So what's going to happen if we cross those two vectors? If we cross those two vectors, we get a third vector that is perpendicular to both of the originals. Now, if we get something that's perpendicular to both of the originals, then it has to be tangent to both surfaces and therefore tangent to the curve. Hence, the cross product of the two gradient vectors for F and G equals T, which is a vector tangent to curve C, and it would look something like that. Okay, now what if we are moving in a different direction? Maybe we don't move along the gradient vector, but we want to move along a different vector. That brings us to directional derivatives. In mathematics, the directional derivative of a multivariate differentiable function along a given unit vector u at a given point p0 in n-dimensional space represents the instantaneous rate of change of the function moving through p0 with a velocity specified by the particular unit vector. And so we have different directional derivatives depending on which way x and y are moving, or more variables depending on the space you're using, for the function, the greatest of which would be if you move along the gradient vector. So here's the formula we're going to use. There are several formulas and there are proofs of each one in your text, but this is the easiest one. So if we want to know the rate of change in f along a different vector other than the gradient vector, we dot the gradient vector with that particular unit vector. Now the reason we use unit vectors is just to keep all our units the same throughout the individual example. Now please note that if we want to know the movement along the I vector, then if we dot the gradient with the I vector, we just get the partial derivative with respect to x, which makes sense because that indicates the movement in the direction along the x-axis along the vector I. Likewise, if we dot with j, if we want to move along the j vector parallel to the y-axis, we end up getting the we just get the second component, the partial derivative with respect to y, and so on if we have a third one. And so this definition is consistent with the meanings of the partial derivatives. Directional derivatives continued. Some notation. Given vector v, made up of n components, and vector x, made up of also n components, and a unit vector, which is vector v divided by its length, that's the unit vector in the direction of v, then the directional derivative of f at the point p0 which would match the vector x, in the direction of the particular unit vector is technically given by this limit. The change along, we add the change along the vector u in our definition of derivative, but it boils down to, and again the proof's in your book, the gradient vector dotted with u. So that's what we're going to use. So number 4 says to compute the gradient vector at the point 3, -1, given f of x, y equals this value. Now they didn't give the z value at that point, and that's okay because we don't need it. So we have to compute the partial derivatives for x and y, and I won't belabor that. You already know how to do that. There's the partial derivative with respect to x, and then with respect to y. Notice the only thing different is applying the chain rule. We get a different tag there. And then, of course, we throw in the values 3 and -1 for x and y. So there's our gradient vector. That's all they asked for. Number 8, compute the gradient vector at the point 2, 1, 0. And again, notice they don't give you the w value because you don't need it. You could, you just don't need it. So this time we need 3 partial derivatives, and these are easy. And after we compute the partial derivative, we put in the values for x, y, or z as needed. So there's the partial derivative with respect to y. Partial derivative with respect to z is a little bit more complicated, not much. And so our gradient vector at that point is just 4, 0, -3. Number 12, compute the directional derivative where the vector u is the unit vector in the direction of v, given this function, this point, and this vector. So we're going to use this formula. So we need to compute vector u, the unit vector in the direction of v, and we need to compute the gradient vector, after which we do the partial derivatives. We have to plug in the values given for x and y for the point p 0, pi/4, and then we dot those two vectors to get our directional derivative. And notice the directional derivative is always a number. This means that there would be no change in z along that particular vector, if x and y moved along that particular vector. Number 18, compute the directional derivative where u is again the unit vector in the direction of v, where the function is given by this expression. We have a particular point, 1, -1, 1, and there's vector v. So again, we're going to use this formula. We compute u by dividing v by its length, and then we want to compute the gradient, which has components of the partial derivatives. And notice that the partial derivatives are all 1 over that quantity, but then the derivative of the inside varies with respect to whichever variable we happen to be taking the derivative with respect to. So you get numerators of 2x, 2y, and -2z. So then we plug in our numbers into our gradient vector and simplify, and then we dot our u vector with our gradient vector, and we get our final answer of 7 over the square root of 17. So if x and y moved in the direction of vector v, then the rate of change in w would be 7 over the square root of 17 units per whatever we're measuring in. Number 22, compute the maximum directional derivative of f at this point given this function. Well, now recall that the maximum rate of change is along the gradient. So the gradient is a directional derivative, specifically in the direction of greatest change. So what they're really asking for is the length of the gradient vector. Maximum directional derivative equals the magnitude of the gradient. So we have 2 partial derivatives, and we have to use the derivative of arctangent, which is 1 over 1 plus whatever the quantity inside is squared. And then because the quantity inside the arctangent was a quotient, we need a derivative of the inside using the quotient rule. And notice that the first time the derivative of y is 0 and the derivative of x is 1, whereas when we do the partial derivative with respect to y, the derivative of y is 1 and the derivative of x is 0. So simplifying that, we get these two expressions, which we then plug in 2 and negative 3 for x and y respectively, and there is our gradient vector at that particular point. The maximum directional derivative is the length of the gradient vector, so we plug that into our length formula or magnitude formula, and we get square root of 13 divided by 13. The maximum directional derivative is square root of 13 divided by 13. Notice that directional derivatives are numerical. Number 30. Use the normal gradient vector to write an equation of the line tangent to the given curve, 2x squared plus 3y squared equals 35 at this particular point. Alright, so here's a picture of the ellipse represented by this function. It's only in two variables there, so it's not a surface. And the gradient vector is perpendicular at the point 2, 3 to the tangent line and to the ellipse then. And the gradient vector has two components. This is like a level curve, you see. And the two components are 4x and 6y, which when we plug in our 2 and our 3, we get 8, 18. And the gradient vector acts as a norm to this level curve. And so there's our tangent vector, by the way. Our tangent vector is just, now see, we're doing this as though it were a plane. We're using the same formulas and method as we did when we were finding the equation of a plane. So we're just pretending it's a plane, but only with two components. And so a plane with two components is a line. And so then we dot n and t. This is pretty cool. And we set that equal to 0. Because if we dot those two perpendicular vectors, we get 0, and then we simplify, and we get the equation of a line. Pretty cool, huh? So we're using our three-dimensional method to do a two-dimensional problem. Now, we didn't need to do that. You could have easily done this last year in single variable calculus using the tools you had then. But this is just to show you that our new tools work on every level. Haha, every level, get it? I killed myself. So now let's do it in where we're used to using this method. Use the normal gradient vector to write an equation of the plane tangent to the given surface, which has an x, y, and a z in it at this particular point. So the method's the same. This time we will get a plane. So here's a picture of, I don't know what the surface really looks like, but we'll just pretend it's some curvy surface, and then the green plane is tangent at that point. And the gradient vector is perpendicular, and so the gradient vector can be used as a normal to the plane tangent to the surface. So we need the gradient vector, so we compute the partial derivatives, which by now you're expert at computing. Then we plug in the particular values at that point, and we're going to use that gradient vector then as the normal to the plane. And then if we want a generic vector on the surface of the plane, it will be x minus 5, comma y plus 2, comma z minus 3, using a generic point x, y, z and the given point. So then all we have to do is dot n with v, because that will be 0 if they're perpendicular. Multiply it out and simplify. And that is the equation of the plane tangent to the given surface above. And so now I leave you with a beautiful picture of a shimmering surface to do the problems on your own. Enjoy!